Following those pioneers of calculus and analysis, Newton and Euler, Martin Heyer is interested in mathematically modeling the evolution of systems that interact, grow, and change. In Martin's case, it is intertwined with probability, modeling the randomly evolving interface between different states, between infected and uninfected, burnt and unburned. Modeling such interfaces can be very smooth and straightforward or extraordinarily complex. In fact, so complex that after many years of study using partial differential equations, we only now understand from Martin that our existing mathematical perspective simply did not include enough details to make precise formulation at all. One of the reasons for this challenge is that these systems, although they exist and interact and need mathematics to model them, involve randomness, and the randomness often breaks the smoothness assumptions needed to get started with the classical approaches. Martin Heyer is a mathematician, and one of the skills of a mathematician is to take things that we do not understand and transform them into concrete, well-defined systems or objects that we understand quite precisely in a certain formal sense. One of the main frontiers in our generation has been to understand the evolution of functions, surfaces, interfaces, and to extend precise mathematical modeling, to extend the notion of partial differential equation, to deal with them. Many mathematicians have worked in this space. Martin Heyer has revolutionized it. I can remember a proposal from Martin early in his career, where he listed several of these challenge problems that have tested great mathematicians for many years. He's since changed the landscape in every one of those problems. Uncertainty and noise and stochasticity expose some of these challenges in the simpler case of ordinary differential equations and Newton's controlled differential equations. Ito's famous theory of stochastic differential equations and then rough path theory provided new insights in that simpler case for understanding this calculus and understanding why it fails without adaptation. In 2011, in a paper in an early one of his revolutionary sequence, Martin showed that the spatial aspects of a one-dimensional nonlinear Berger equation needed these insights before it could be well formed. And then in a stunning series of papers, he built regularity structures, combined them with renormalization, and created a framework needed to understand these famous challenge problems, and much more. Completely rewriting and making precise our understanding of nonlinear SPDEs, such as the KPZ equation. Aside from the brilliance of his achievements, his 2014 Fields Medal, his 2021 Breakthrough Prize, I've heard Martin give some great talks to audiences like this one. So it is with much excitement and anticipation that I now hand over to Sir Martin Heyer from Imperial College London to present his lecture, A Mathematical Journey Through Scales. Thank you, Martin.
Thank you very much, Terry. Thanks a lot for the very kind introduction. Would first like to start by thanking the organizers also for the invitation. It's a pleasure to be able to give this public lecture, this Hirzebruch lecture, at this somewhat special edition of the European Congress of Mathematics. And what the topic of my talk is going to be scales and how systems change under changes of scales. And so I thought that to start, I would show you a little video. So it's a video that was made by an Australian physicist, Daniel Obreshkov, called Cosmic Eye, and it would give you a little bit of an intuition about the size of these scales. So here, what we do is we start with a picture of the nucleus of an atom, and we're zooming out. So what you see here is every few seconds, we zoom out by a factor 10. So now the nucleus becomes very small. What you see here is the cloud of electrons that's around the nucleus. And now you see that atom inside of a molecule. You see it's a molecule of DNA. If we keep on zooming out, we start to see, the DNA curled up inside of a cell. We see that it's a white blood cell inside of a capillary. We zoom further out, we see that it's actually in the eye of a person. And now we get to our human scales of about centimeters. And now about a meter, we're zooming out. We see that the person is lying in a field, in a city. And now we're getting to very large scales, right? So we see that the city is on the west coast of the United States. And now we're already at the scale of the whole Earth. We see the Earth sort of receding in the distance. And now just a few scales up, we're at the scale of the whole solar system. And we keep on zooming out. So now we're seeing the end of the periphery of the solar system, which is about a few billion kilometers wide. So here you saw Voyager, the first Voyager probe that was sent out in the 70s. And now we're getting to the nearest stars at a few light years. And if we zoom further out, we see we're going to see the Milky Way, right? So at a few thousands or hundreds of thousands of light years, we're at the scale of galaxies. And then a few scales further up, we're at the level of galaxy clusters. And now we're at the level of superclusters of galaxies. And one more scale up, we're actually at the scale of the entire universe. So what we saw here is that the size of the universe, at the end of the day, is actually not that many scales, right? So what we've seen is that it just took a couple of minutes to zoom from the smallest features that we know about, which is the quarks inside the nucleus of an atom, up to the size of the whole universe. And so the factor is about 10 to the 40. So we would call that 40 orders of magnitude. You can do the same in time. So if you compare the longest duration that we know, sort of the age of the universe, to the shortest duration that we know about, so like the vibrations inside of an atom, you'd see it's about 30, between 30 and 40 orders of magnitude. So what this tells us is that in some sense, numbers that are bigger than about 10 to the 150 or so, they're essentially infinite for all practical purposes, in the sense that there is nothing in the universe, there is no ratio bigger than about 10 to the 100 that would naturally appear anywhere in the universe. On the other hand, many of you have probably heard very often about the famous sort of monkey's paradox, where you say that, well, if you put a monkey in front of a typewriter and you let the monkey type for long enough, at some point, the monkey will type the combined works of Shakespeare. Now, just to give you an intuition about, how much more unlikely this is compared to the sort of orders of magnitude that actually arise in the universe. Well, if you're content with just one page of Shakespeare, not the whole works, but just one page of Shakespeare, and you ask yourself, how many characters do you have to type before you see a page of Shakespeare by typing randomly, you'd actually have to type about 10 to the 4,000. So that means that even if the universe was a giant neutron star, so it was completely filled with matter, even though it's actually mostly empty, and every single atom there was like a monkey typing, and it types sort of at the speed of its natural frequency, and you let that running for the whole duration of the universe, well, the number of characters you would have typed is about 10 to the 100, right? And so you would need still billions and billions of these universes, and you would still have absolutely no chance of seeing a page of Shakespeare. Right? So this is just to give you an idea that when you start to look at kind of combinatorial, the number of possibilities of sort of like combinatorial objects, you quickly end up with numbers that are actually much larger than any sort of number that would naturally appear in the universe. Now, what we'd be interested in changes of scale. And we've seen in the movie that at different scales, the universe looks very differently. And the reason is that, well, the laws of nature, they are not linear. And so they actually change, or the behavior of the laws of nature changes when we change scales. So for example, if you look at the surface of a pond, or just, you know, any kind of water, if you look at it at small scales, like the scale of these little insects, well, it looks quite differently. You see, these little insects, they are perfectly able to walk on water, whereas humans, well, at least usually, they are not able to walk on water. And so the reason for this is that at small scales, liquids appear much more viscous. So in a way, water at very small scales behaves much more like honey would behave at our scales. And they also have much higher surface tension. So the surface of the water appears to be much more solid, if you want, at small scales. And that's what allows these little insects to just walk on water as if it was a solid surface. If you now imagine, take an example of just a picture, and we look at what happens when we change scales, then, well, you know, if you take a picture like this pot of tea here, and you change scales, what does it mean? It just means zooming in, for example. So if I zoom into that pot of tea, well, what you see, you know, it gets pretty boring very quickly, right? I mean, in most places where I would zoom in, after a while, I actually just see a plain color. Or maybe I could see something slightly more interesting if I zoom in just at the border, at some border, and then I would just see two plain colors. But still, it's not very interesting, right? You've lost all features here when you zoom in. On the other hand, there are some pictures that show up naturally in mathematics that have a much more interesting behavior when you zoom in. So this here is a picture of what we call a fractal. And this is probably one of the most famous fractals, which is called the Mandelbrot set, which was discovered by Mandelbrot in the late 60s. And so here, if I zoom in, well, this is this Mandelbrot set. I zoom in around here, I see this kind of picture. If I now zoom in into one of these spirals, it looks like that. If I zoom further into the spiral, it looks like this. If I zoom now into one of these bright spots, it looks like that. And you see again, inside these bright spots, you have more little spirals. So I can again zoom into this spiral. You see again, more of these bright spots, etc. So here I can actually zoom as long as I want, and I see details at every scale. So for example, if I zoomed further into that spot in the middle, I would actually see a full copy of the whole Mandelbrot set itself hidden in this spot. So there are these very interesting objects, if you want, where I can zoom in, you can zoom in or zoom out as much as you want, and you would still see details. Okay. Another example, which is, if you want, more closely related to what one actually does in mathematical modeling, would be the Lorenz system. So the Lorenz system was invented, if you want, by Lorenz in, I think, I'm not sure it was, I think it was also in the late 60s. And it's a very simplified model for atmospheric convection. And so it's a system of 3 differential equations. The main feature, so these equations are very simple. The main feature is that they are nonlinear. So you see here, there is a quadratic term. There's a product, x times y on the right-hand side. And here there's this x times z product. If you plot solutions of this system, it kind of looks like this. So here is a plot of one of these. So you have 3 components, x, y, and z. So you pick 2 of them. I don't remember which 2 of them it is, maybe x and y. And so then you plot, say, x horizontally, say y vertically, and you look at it as a function of time. And what you see is as a function of time, you get a trajectory. And what it does is it sort of spirals around. You see there are two fixed points here. It spirals around these points and then occasionally switches over and then spirals around the other point, and it switches over again and so on. And if you try to predict so this trajectory, of course, you can solve this equation on a computer. Everything is completely determined by the initial condition. If you fix a starting point, then in principle, you can exactly predict the trajectory of the system. But in practice, you actually can't, because it has this chaotic behavior, which tells you that if you want to predict the precise trajectory, then you can't really do that beyond a few revolutions. And the reason here is that, well, one can show that the precision that you would need at time zero, right? So the precision at which you would need to know the initial data at time zero, in order to predict with certainty, say, around which lobe the solution finds itself after some time t. So that precision is about 10 to the minus t over 2, roughly, right? 0.4 times t. So, and it takes about time 1 to switch sort of from one lobe to the other. So you see that like 10 switches is about okay, because that would require you to know the initial data with precision of 10 to the minus 4, which basically just means you need to know about 4 digits. But then if you want to predict to, like 100 or 1,000 revolutions, well, then it would mean that you would need to know your initial data up to a precision of, 10 to the minus 200 or 10 to the minus 300. And what we've seen in this movie that I showed you at the beginning is that, well, it's impossible to measure anything at a precision of 10 to the minus 200, right? So 10 to the minus 200 is already much, much smaller than the ratio between subatomic particles and the whole size of the universe, right? So there's absolutely no chance. And so the question is, can we still say something about the behavior of large times, right? So we can certainly not predict the behavior for sure. If you ask, even if I give you the initial data, it will always have some error, and so it's going to be completely impossible to predict around which lobe the solution will find itself after, say, time 100. So here is what happens if you plot, for example, take one of the coordinates of the Lorenz system, say the first one, the x coordinate, and interpret that coordinate actually as a velocity, and then plot the corresponding position, right? So this coordinate would be the coordinate, the horizontal coordinate here, which is sometimes positive when you find yourself around this lobe, and sometimes negative when you find yourself around this lobe. And that means if you interpret this as a velocity, positive velocity means of going up, negative velocity means going down. So if you look at the corresponding position, you end up drawing a curve that sometimes goes up, sometimes it goes down, just depending on whether the solution finds itself turning around the right lobe or the left lobe. So this is what happens sort of after time 5. You see there's about five or 6 revolutions. You see that it changes lobe when you change direction here. This is what it looks like after time 50. And this is what it looks like after time 500. And this is what it looks like after time 5,000. So one thing that you already start to notice, so of course it looks completely random, but on the other hand, if you look at the picture here after time 5,000 and you compare it to the picture after time 500, the two pictures actually look very similar, right? Because I've somehow rescaled them so that they are drawn in the same screen, so they have about the same size. But actually, if you look at sort of how fast, this curve sort of moves up and down, how jittery it is in a way. This picture actually looks quite similar to this picture. And now you can compare it to a very, very simple model, right? So we could imagine that, well, if we don't know around which lobe the solution is going to find itself after, any sort of large moment of time, then why don't you take as a model the one where we just say, well, it's just going to be completely random. So if like after every time step, I just find myself around one of the two lobes completely randomly. And that's basically the same as saying, well, I flip a coin, and then if it comes up heads, I say I win a pound. If it comes up tail, I lose a pound, and then I plot the amount of money I have as a function of time. Okay, assuming that I don't go bankrupt, so I'm allowed to have negative money. So, you get something like this, you throw heads twice, then tail, and so on. So you see that you start to see something that looks, well, you have this random walk, which looks actually quite similar to what we saw for the solution. So what does this look like after a large number of games? Well, if I do this 3,000 times, you see something like that. And if you compare this picture to the one that we saw from the Lorenz system, you see they really look very, very similar. So they have very similar qualitative features, these curves. So they both look very rough, but you can actually make statistics on them. You actually find that they obey essentially the same statistics. And so, for example, a very simple statistic here is you can ask yourself, typically, how much money are you going to have after about n games? And that is given by what's called the central limit theorem, which tells us that you would have about, square root of n plus minus. So it doesn't mean you win. You might also lose about square root of n, but it's very unlikely that you would win much more or lose much more than about square root of n pounds after n games, right? So we know how to do statistics on these random curves. And you see here that there is a kind of nice limiting random curve, which we call Brownian motion. And so Brownian motion, to some extent, well, it was first discovered experimentally, actually, by Brown. And so that's why we call it Brownian motion. And so he observed pollen suspended in water. That was back in the 1840s or 1850s, something like that. And what he noticed is that when you look at these pollen particles suspended in water, they actually move in a sort of erratic way, even though, there is no external influence, right? So even though he left the water overnight, completely isolated on a table that isolates from vibrations, and still when he came back next morning, the little pollen particles were moving erratically in the water. And well, so for some time, it was a challenge to actually explain this, because in the beginning, he thought it was actually alive, that what he was seeing were kind of little bacteria or something. But he figured out pretty quickly that that wasn't the case, that they were not alive. And so the explanation that was given, and in some sense, it was made more quantitative in the early 20th century, independently by Einstein and by Smoluchowski. So from the physical point of view, the explanation is that the erratic motion of the particle that you see is caused by collisions with water molecules. And so the explanation is you should imagine somehow the water molecules as being like little billiard balls that kind of move around in a, well, sort of basically in straight lines, the way that billiard balls would move around, and then they collide and they somehow So that means that because of the collisions, they perform themselves some erratic random motion. And every time this great pollen particle collides with a water molecule, well, it gets a little push. Of course, a water molecule is tiny, so it gives it a very small push, but there are many, many water molecules, and they move relatively fast. So somehow the average velocity of these water molecules is actually what we call the temperature, right? So the warmer the water, the faster they move. And that's why there is an absolute zero temperature, right? So the absolute zero, which is not the freezing point, the absolute zero is the point where they don't move at all. So you have these molecules of water that bombard your pollen particle, and there are so many of them that the net effect of this bombardment is actually visible under a microscope. And Einstein and Smoluchowski were actually able to make quantitative predictions from that, because it was already known, if you want, how many molecules you would expect in a given quantity of waters and how fast they would move given the temperature and so on. So these type of quantities were already known, except that it was not at the time completely accepted that matter is really made of atoms and molecules, right? So that was at the time, it was the dominant hypothesis, but there hadn't been any experiment that would actually not have any other explanations than the fact that matter is made of atoms and molecules. And so this simple experiment of the little particles suspended in water, with Einstein and Smoluchowski's prediction, it actually allowed you, so they actually gave a quantitative prediction of by how fast these molecules would move, depending on their size, and on a number of other quantities that you could actually measure. And Perrin, in 1908, he did the experiment very carefully, and he found very good agreement with the predictions. And so that then really closed the debate regarding the existence of atoms. And what Einstein and Smoluchowski found is that also mathematically, if you wanted to describe this Brownian motion, so on the one hand, if you look at the position of these particles as a function of time, again, it's a very erratic curve, which looks very much like this. And actually, in some sense, it is the same, in the sense that it would have the same statistical properties. And mathematically, if you want to describe the distribution of such a random curve, it's very closely related to an equation called the heat equation, which was actually originally developed to, well, as the name suggests, was developed to model the propagation of heat in a solid body. Now, interestingly, around the same time, just a little bit earlier, Bachelier, who was a young probabilist in Paris, he submits his thesis called Théorie de la spéculation, where he was interested in the evolution of asset prices, like stock prices on the stock market. And he had, well, in his thesis, well, interestingly, so first, he didn't actually find much recognition for his work, at least not until very much later. But somehow the probabilists at the time did not somehow have finance as a motivation for a mathematical model. But so what he did in his thesis is he describes a mechanism for the evolution of stock prices, which is somehow very similar to the mechanism that Einstein and Smoluchowski described, in the sense that what he says, well, the stock price is influenced by the individual people buying and selling shares. And every time someone buys a share, the price goes up a little bit. Every time someone sells a share, the price goes down a little bit. And of course, any one individual buying or selling shares is going to have a very tiny effect on the stock price, but there are many, many individuals that buy and sell shares more or less simultaneously. And so the total effect is visible in the fluctuations of the price. And he derived, mathematically, he derived the equation that describes this. And again, he came up with the heat equation. So you see what's interesting here is that you have two completely different situations. So on the one hand, the particles of pollen suspended in water. On the other hand, the evolution of stock prices. But the mechanism at an intuitive level, the mechanisms are similar. And from this intuitive description, you can derive a mathematical description, and you end up with the same mathematical description, maybe not too surprisingly. So this then, in terms of, so Bachelier's work really kind of laid the foundations of modern mathematical finance, if you want. In particular, it really laid the foundations for the works of Black and Scholes, who got the Nobel Prize in economics for that. Bachelier, well, basically didn't get a job until the age of 57, unfortunately. So here, what's the situation? So what's kind of interesting is that, you know, we are in the situation where if we take a kind of intuitive perspective and see, well, at a sort of rough level, these two very different situations would actually be described by a very similar, or by the same equation actually, because they have very similar mechanisms. But if we wanted to describe them more precisely, right? So if you wanted to really describe what the motion of a particle of pollen in water does, and on the other hand, if you wanted to really precisely describe, so for precisely look at the evolution of stock prices, then you actually see something quite different. So at the microscopic level, you have two very different models, but by the time you look at what happens at large scales, they actually look the same. So the same as the Lorenz model is a very different model from simply successive coin tosses. But when we looked at it at large scales, they actually look the same, right? And so Wilson, back in the 80s, so that's a picture of Ken Wilson. So he, if you want, so he promoted the following perspective. So what he said is you should really think of all possible physical models or mathematical models as being some kind of big space. So there's a space of all mathematical models, or maybe all mathematical models that are plausible for a given situation. And then you should think of the operation of zooming out as being a flow in this space of mathematical models, right? So now you would say, well, you know, if I take a model and I zoom out, it's still the same model, so the model hasn't changed. But it has changed because you changed, if you describe the effect of the model at scales of order 1, then that would be different, right? So it's like there's one model, which is the Navier-Stokes equations that describe fluids. But then depending on when you look at the Navier-Stokes equations at small scales, well, it behaves in a very viscous way, or at large scales where it behaves in a very non-viscous way. So at different scales, the same model behaves very differently. And so you should think of it as a different model, right? And you should think of then the operation of zooming out as being like a curve in the space of models, so a dynamical system in mathematical terms. And what Wilson then, the idea that Wilson promoted is that then the interesting points in that space of models would be the fixed points, right? So that would be those models so that you can zoom out as much as you want, it always behaves in the same way. And then you can, ask yourself, what is the basin of attraction of these fixed points? So what are those models, like this one here, which have the property that as I zoom out, they converge to one of these fixed points, right? If they converge to something, they have to converge to a fixed point. And so that's somehow the reason, if you want, why these fixed points would be interesting. And then given such a fixed point, all the models that converge to the fixed point under the operation of zooming out is what we would call a universality class for this fixed point. And so Brownian motion is one of these fixed points, right? So Brownian motion has the property that you get these kind of jiggly fractal curve. Actually, you can zoom in and out of this curve as much as you want. It always looks the same, right? It always has the same statistical properties. So it is one of these models that doesn't change under the operation of zooming out. So it is a fixed point in the Wilsonian point of view. And to some extent, that's sort of one of the reasons also for what Wigner called the unreasonable effectiveness of mathematics. Right? So one reason why mathematics is sort of effective at describing reality, if you want, is that there are many situations where the very messy microscopic details of a system don't actually really matter. And as far as the behavior at larger scales is concerned, you can actually replace them by a much simpler toy model. So here I want to give you an example of a system which is not in this Brownian universality class, right? So far the examples that we've seen always somehow at large scales end up being described by Brownian motion. So here the example is that of interface fluctuation. So you should think of two regions that have different stabilities and an interface that separates the two. So for example, here you see a forest fire. The interface here is the flame front. The two regions that it separates, it's the region that has burned and the region that hasn't burned yet. And clearly, this region is somehow more stable than that one because the front is going to move in this direction. So once, if you want, once the forest has burned, it cannot unburn. But the bit of forests that hasn't burned yet, that one can still burn, right? So you can move from being unburned to being burned, but you cannot go back from being burned to being unburned. And so the interface that separates the two necessarily will move in this direction, right? So it's going to have some kind of average speed. But then what's interesting is you see that it has these random fluctuations here that come from the fact that some bits move a bit faster, some bits move a bit slower. And so what mathematicians are interested in is the description of these random fluctuations. And there are other systems of the same type. So here is actually a photo of a liquid crystal that comes in two different phases. One is more stable than the other, and the stable one invades the unstable one. And another example here is what I call the Tetris model. I can actually show you what this looks like. So here you just imagine that you play the Tetris game. So here you see the Tetris bricks piling up on the screen. So you just imagine Tetris bricks falling down from the sky, and they just pile up as they do in the Tetris game, except that you don't play the game. So they just pile up randomly. And now we can look at what happens at larger scales, right? So here we see bricks at the bottom, no bricks at the top, and you see the interface between the two. And this interface is not quite flat, right? So you see that it's more or less flat, but it does have these fluctuations. Here again, so you see now at larger scales, you see these random fluctuations of this interface, and you would like to have a mathematical model that describes this. And again, intuitively, one would imagine the model to be the same for all of these situations, actually. So in this particular case, it turns out that there are actually two relevant universality classes there is one, well, in the situation that I just described, the relevant one is the KPZ universality class, which is named after Cardar, Parisi, and Zhang. Somehow, if you want, not quite describe, they didn't describe it completely, but at least described some of its features back in the mid-80s. And there's also another relevant class, which appears in the situation where the interface can actually move in both directions. So the examples that I gave you, the interface moves in one direction. You can have situations that are symmetric also, where it can move in both directions. And in this case, the fluctuations actually behave differently. And that's described by what's called the Edwards-Wilkinson universality class. And so you have these two fixed points, or if you want, the picture is somehow there's a symmetry axis, so that one naturally shows up twice, once for interfaces moving up and once for interfaces moving down. And well, Wilson's intuitive picture that we should have in mind is that any of the three models that I just showed you, that would be, you know, some model, some interface model here, but as you zoom out, one would expect it to converge to some kind of universal interface model, which would be this KPZ fixed point here. And that universal interface model, it turns out, is actually much more difficult to describe than Brownian motion, for example. And this is actually a very recent result from just a few years ago by Matetsky, Remenick, and Postel, which in some sense I could formulate it informally as saying that the KPZ fixed point actually exists, in the sense that there is one specific model, which is not one of the three models that I showed you, but you know, often a little bit similar to the Tetris model, but kind of a bit different, which has the property that as you zoom out, you can actually completely describe what the limit is. And then the conjecture is that all of these models have the same limit as you zoom out. But that's still something which is mathematically not known at all, right? So in the case of Brownian motion, we have many mathematical theorems that go along the lines of, you know, random curves or random evolutions with this and that property, when you look at them at large scales, are well described by Brownian motion. There are many mathematical theorems with that flavor. Here in this example of this KPZ fixed point, we are only at the stage of actually being able to describe what the limit should be. But there are very few theorems along the lines of, you know, take this model and zoom out, then it actually converges to that limit. So one thing which is actually much easier to describe is this Edwards-Wilkinson, so the symmetric case, if you want, because there the limit is what we call Gaussian. In some sense, the description is very similar to the description of Brownian motion. So it's very explicit and very simple. And so it's much easier to actually prove that some symmetric interface fluctuation model converges to this Edwards-Wilkinson fixed point. And so we can ask ourselves, you know, is there a connection between the two? So is there like a natural model that connects the Edwards-Wilkinson model, the Edwards-Wilkinson fixed point, to the KPZ fixed point? And here the conjecture, if you want, is that such a model exists, and there's exactly one. And that model is what we call the KPZ equation. So I don't want to go into the details. So here I wrote down what the equation is. So some of you in the audience will know what I mean by this. If you don't, that doesn't really matter. The important point here is this term, which involves the slope. So here H is, you imagine this interface, you think of it as a function. So there's X here, and you plot H, the location of the interface, as a function of X and time. And so the derivative here is the slope, right? So the slope, if you want, the value of the tangent. And in this equation, you have the square of the derivative appearing, and you have some noise term appearing here. So this psi somehow represents noise, if you want. And a problem of this equation is that solutions end up being extremely irregular. And so that means that this slope here is actually infinite at every point. So in this idealized model, which of course by itself is not really a good model for any physical situation, but it's a natural idealized mathematical model that many other models converge to when you look at them at the right scales. Then in this idealized model, the slope is actually infinite everywhere. And so the equation in a way doesn't really have any meaning, right? And so what you want to do is you want to really interpret this in a way where there's some kind of infinite constant here that gets subtracted. And one of the contributions over the last few years, which Terry mentioned in the introduction, is, and which also builds upon his work, is to develop a theory of solutions for this type of equations. And here are the names of some of my co-authors who were active in developing that theory. And the point here is that you want a theory, you don't just want the notion of solution because you say, well, you know, this is some sort of idealized mathematical object. It's nice to know what this object is, to have a way of describing it. But you also want to know that this object is somehow stable, so that there are more realistic models that in certain regimes converge to it. And it turns out we have some notion of stability, so which goes very much, we have also in particular with the result with Jeremy, we can go towards proving, or at least having theorems that very much support this intuitive picture, which would say that there is exactly one line here that, if one connects this Edwards-Wilkinson model to the KPZ fixed point, right? This is not obvious because this is, of course, a cartoon. You should think of this as the space of all models of interface fluctuation, which is not at all two-dimensional, right? In 2 dimensions, of course, the only way of joining 2 points is by a line. In higher dimension, you could join it by, you know, some kind of a surface. For example, you could have like a surface that looks a bit like a leaf with, you know, 2 singular points at either end that would be these fixed points, right? But the conjecture is that it's really a line, even in the space of somehow all models. And there's some progress now that's been made in this direction. So I think I stop here, and I hope I've, you know, given you some kind of idea of what are, you know, some mathematical problems that people are thinking about, and how, you know, there are some problems that appear not too difficult, like, you know, looking at the behavior of this Tetris bricks falling down, that are actually still, you know, quite a bit at the forefront of sort of modern mathematics, and there are still lots of things to do there. Thank you very much.